All right, so if we pick up where we left off, we're looking at rate laws. Again, this is the generic, or this is our format for a rate law. The rate of our chemical reaction is equal to K, which is just our rate constant. We'll talk more about that later. Times the concentration of your reactants. In this case, those were the two reactants. And then our reactant is going to be raised to some power. And so we see the power here is 1. So when the power is 1, we don't write the number 1. It's understood. It could be a 2, a 3, a 4. But we see here the exponents, both here are 1. And so we would say that it's first order with respect to each reactant. And we'll get more into that here in a second. Again, the order of the reaction, that's what the exponent tells us, the order of the reaction with respect to each reactant. So since we have this rate law here, then it's first order in NH4 plus, so brackets again, remember mean concentration, and also first order in NO2 minus. And so it's going to be very important that we are able to write the rate law and then that we are able to understand the order. Now, today we're going to look more at why is it first order and first order. So what about the data tells us that it's first order? Here are a couple there's a few examples of rate laws. So the rate law for this reaction is here. So you see rate equals K times the concentration of your reactant. Your reactant here is N2O5. Rate equals K times the concentration of your reactants raised to some power. The power is here. We see our 1.5. And then here we have rate equals K times the concentration of your reactants. Again, power is 1 and 1, so the first order and first order. I show you this to show you that we don't just assume that the coefficients from the balanced chemical reaction are the exponents. So this is a 2, but we don't have a 2 here. This is a 1, and there's a 1 here, but this is not a 1 because that's a 1. We'll talk more about why we get the exponent of 1 here in a second. And so how do we find the order of the reaction based off initial experimental data? And so this is going back to what we just looked at. And so when I look here, I'm trying to see what about this data tells me it's first order. And so what we're looking at is we are looking at the initial concentration. So if we just focus on NH4+, we notice that when the initial concentration of NH4+ doubles, right, so it goes up by 2, the rate also doubles, right? So there's the same relationship between initial concentration and observed rate. So when we have the same relationship like that, we would say it's first order. So when concentration doubles and the rate doubles, that's first order. What would second order be? Well, if the exponent was 2, that would mean when the concentration doubles, this would then quadruple. But we see doubles and doubles, so it's first order. Same thing we see down here. This right here, this concentration is staying the same. This concentration, let's say 4 and 5, is doubling. And so then the rate is doubling as well because the concentration doubled and the rate doubled. That's the same effect. Then we know that it's first order. So that's a more conceptual way. That's one way to think about it. Again, if this rate had doubled, or the concentration had doubled, and this rate went up by a factor of 4, it wouldn't be first order, it would then be second order. And so that's the conceptual way to think about it. Now I'm also going to show you a mathematical way to think about it. So if you can just kind of take a picture of this, screenshot it, have it off to the side, put it in your notes. I'm going to use this data. I'm not going to have it up, but I'm going to be referring back to this data table to help us understand how to mathematically solve. So there's a conceptual way of looking at it, but these numbers are easy to look at. These numbers are easy to work with, right? 5.4 times 2 is 10.8. Easy to work with, but your numbers are not always going to be easy to work with. So I'm going to show you the mathematical way. You can follow the same process every single time, but it's more so using a formula. So make sure you have this data table, and we'll look at it here mathematically. Okay, so to solve for the order of the reaction mathematically, we're always going to start with the rate law. So we know that when we have a rate law, it's K times the concentration of my reactant. So when in this case, it's NH4+, and the concentration of NO2 minus. I'm going to put X and Y there because, again, We already know x and y are both going to be 1, but now I'm going to show you mathematically why. So we'll start with our rate law. Rate equals K times the concentration of both of our reactants raised to a certain power. And now what we're going to do is we're going to pick 2 experiments, and we're going to look at experiments where one of the concentrations is changing and one is not. So I'll just pick experiment number 1 and experiment number 2 to solve for this. Now, when I do this, I'm going to put rate 2 divided by rate 1. So for me, I always put the bigger numbered rate. So if you look at observed initial rate on the far right, I always put the bigger one on top. That's why I'm putting rate 2 over rate 1. So I'm saying the rate of experiment 2 divided by the rate of experiment 1. Now, when we write our rate law, rate equals K times the concentration of my reactants raised to a power, and it's going to be the same thing for rate 1. So experiment 1, so we're just writing both rate laws and we're dividing them by each other. So I've got rate 2 over rate 1. I've got the rate law for the first, rate law for the second, and rate law for the first on the bottom. Now from here you can just go plug in all the numbers that you're given from the table. Now we know, when we look at this, we know that K, the rate constant, is not changing. And so if we have the number that's not changing, it's going to be the same on the top and the same on the bottom. We can cancel it out. And so K would cancel out. We also see that the concentration of NO2 minus is not changing. It's going to stay the same, so we can cancel that out. So we're left with rate 2 equals the concentration of NH4 plus to the X divided by rate 1 equals the concentration of NH4 plus to the X. Again, what we're trying to solve for is X. We're trying to figure out what is that exponent so we can then know what the order is. And now we know the rates for there. So the rate for experiment 2 is 10.8 times 10 to the negative 7. The rate for experiment 1 is 5.4 times 10 to the negative 7. Now, one thing we can do here to simplify this, right, we can plug our numbers in first. So let's go ahead and plug the concentration of NH4 plus in experiment 1 and 2. So we're going to get 0.0200 divided by 0.0100 raised to the X. Now I can simplify this, so I can rewrite this, and I know that this divided by this is 2, and I can rewrite this as 0.0200 divided by 0.0100 to the X. Now, from there, what is that going to give me? Right, so that's an arrow, sort of. That's going to give me 2 equals 2 to the X. Now you look at it for what number. You could use logarithms if you want to solve for this for X, but I just look at it and say, what number does X have to be for this statement to be true? Well, we would say that X has to equal 1. Now, what we would have to say is it's first order, and I use WRT, which stands for with respect to. So first order with respect to what? And X was on NH4 plus. So I say it's first order with respect to the concentration of NH4 plus. And so that's how we know this exponent up here is 1. Again, we're comparing kind of the ratio of the rates to the ratio of how the concentration is changing. Based off that relationship, we're going to know what the exponent should be. Because this doubles, when this doubles, this also doubles, we know that it's first order. And so we have X, and now we can solve for Y. So if we want to solve for Y, we have to use 2 experiments where this concentration is changing, but this is remaining the same. So you could pick 4, 5, or 6, any combination there. I'm just going to pick 4 and 5. So what I do is I'll say that rate 5 over rate 4. Again, I'm picking 5 because experiment 5 has the larger rate, and that's K, concentration of NH4 plus. Now, or times the concentration of NO2 minus to the Y. I don't have to put an X here because we know that it's 1. And then K, concentration of NH4 plus, NO2 minus to the Y. And so we're going to try to solve for Y. K remains constant. The concentration of NH4 plus in experiment 4 and 5 is not changing, so we can mark that, cancel that out. We can then write in rate 5. So we now know that rate 5 is equal to 21.6 times 10 to the negative 7 divided by 10.8 times 10 to the negative 7. And that's going to equal concentration of NO2. So we're going 0.0404 divided by 0.0202. So we divide those and I get 2 equals. Remember, you can rewrite this to the Y. You can simplify that. So then we would then end up with 2 equals 2 to the Y. We know Y has to equal 1 for that statement to be true. So we know it's first order with respect to the concentration of NO2 minus. Now, if you got, so now we can see that these are both 1s. So that's why when we write the rate law, we write rate is K concentration of NH4 plus times NO2 minus. And so we can see this set up. If you doubled this, because that's an exponent of 1, if you double this, the rate doubles, which is what we expect to happen. Same thing here, if you double this, the rate would double, and because the exponent is 1. So when we look at the exponents just tell us the order. We're going to learn later on, this knowing that's first order will tell us other things down the road. But for now, you need to be able to write the rate law. Rate is K times the concentration of your reactants, and then you got to be able to know what the exponent is going to be. And so this is the mathematical way to solve. We just talked about the conceptual way. If you understand the conceptual way, you can use that method. You just have to write an explanation and saying, in experiment 2 and 1, the rate doubles, and so because the rate doubles and the concentration doubles, I know it's first order. You can write a sentence or two explaining that, and that's proper justification. This is also proper justification as well. So again, right now what we're working on is we're working on how do we write our rate law, how do I find the exponent so I can then know the order of the reaction with respect to each reactant. And I would tell you if you're answering what's the order, you have to write this right here. You cannot say X equals 1 and Y equals 1. You've got to write this statement as well. So make sure you go that far and make sure you include that. So now you're going to work a couple practice problems where all you're doing is writing the rate law, solving for the order, and then we'll move on later this week with more calculations.